It started with a whisper, a barely noticeable distortion in a sea of spectrographic data, dismissed at first as background noise. A glitch, perhaps, in the cascade of photons filtered through alien atmospheres. But this wasn't just noise. This was a whisper from a distant world. K218b, a planet 124 light-years away, orbiting a red dwarf in the constellation Leo. A whisper that grew louder when quantum AI got involved. That whisper became a message we weren't sure we wanted to hear. At first, it was just another routine data set from the James Webb Space Telescope. The instruments, NIRSpec and NIRIS, had been focused on K218b during a transit, watching the starlight bend and scatter through its atmosphere. Scientists expected to confirm water vapor, maybe pick up traces of methane or carbon dioxide, standard atmospheric signatures. But as the data streamed back, nothing seemed extraordinary. That is, until it was run through a next-generation quantum AI system built in a private lab in Geneva. This wasn't just a powerful computer. This was a fundamentally different kind of intelligence. It wasn't trained like traditional machine learning models. It was forged in the entangled chaos of quantum states, designed to see patterns across data dimensions we can't even name, let alone comprehend. Trained on exabytes of planetary atmospheric data, terrestrial chemistry, and a library of known and hypothesized biosignatures, this quantum AI wasn't just looking for molecules. It was listening for harmony, resonance, balance. And what it found sent shockwaves through the astrophysical community. The AI flagged 3 distinct chemical patterns: methane, dimethyl sulfide, DMS, and carbon dioxide. But that wasn't what made this disturbing. It was the 4th signal, a weak but consistent presence of dimethyl disulfide, DMDS. On Earth, DMS and DMDS are produced almost exclusively by marine microorganisms like phytoplankton. These molecules aren't the kind of thing you'd expect to find from volcanic activity or exotic chemistry. They're byproducts of life, of metabolism, respiration, decay. But DMS alone wouldn't be enough to make such a bold claim. So the AI looked deeper, breaking the signal into quantum time fragments, isolating chemical harmonics correlated with pressure zones in the atmosphere. It identified wave functions in the spectral data that indicated these molecules weren't isolated, weren't random. They were part of a system, a cycle. The sulfur compounds showed correlation with methane concentrations, which themselves shifted in patterns consistent with biological emission and breakdown. The carbon dioxide wasn't uniformly distributed. It clustered in regions that matched expected upwelling from a deep ocean below a thick hydrogen-rich atmosphere. That's when the whispers became voices. The research team at Cambridge University, working in collaboration with the Geneva lab, published a preprint detailing what they believed to be a strong case for a living biosphere on K218b. Their hypothesis: microbial life in a global ocean beneath a hydrogen cloud layer could be releasing DMS and DMDS into the atmosphere, just like phytoplankton do on Earth. The resemblance was uncanny, not just in molecules but in ratios, timing, even diurnal fluctuation patterns. The reaction was instant. Some called it the most important data set in the history of exoplanet science. Others were more cautious, arguing that extraordinary claims demand extraordinary evidence. Still, the data was there, and the AI kept finding the same story again and again, no matter how it was sliced, randomized, or noise-stripped. But not everyone was convinced. Within days, a rival team at Oxford conducted their own independent review of the same JWST datasets. Using traditional spectrographic modeling techniques, they couldn't replicate the DMDS detection. They found methane, yes. Carbon dioxide, yes. But the sulfur signals, so prominent in the quantum AI's analysis, were nowhere to be found. The Oxford team argued that the supposed DMS signature could be an artifact, a misread, a spectral glitch amplified by overlapping zones in the telescope's sensors. Worse, they warned that the AI might be overfitting, drawing meaning from randomness, a mirage in a sea of uncertainty. It sparked a furious debate not just about the planet, but about the technology used to analyze it. The Oxford scientists questioned whether quantum AI, despite its power, might be fundamentally opaque. If even the researchers who trained it can't fully understand how it sees patterns, can its results be trusted? It's not that it's wrong necessarily, it's that it might be right in ways we don't yet comprehend, and that makes its conclusions slippery. Alien. Alien not just in subject, but in process. Still, Cambridge stood by their findings. They argued that the AI didn't just spot isolated chemical traces, it found interlinked spectral resonances over time. The DMS wasn't detected once. It pulsed through the atmosphere in time-locked patterns, like breathing, like a heartbeat. It wasn't just chemical, it was rhythmic, living. As the debate raged, a leak from the European Space Agency added fuel to the fire. According to an anonymous source within the ESA, preliminary data from JWST's mid-infrared instrument, MIRI, had been quietly showing signs of something else. Ammonia. Trace amounts, barely above the detection threshold, but consistent across multiple passes. On Earth, ammonia is a biosignature molecule, commonly exhaled by oceanic microbes. But in K218b's hydrogen-rich atmosphere, ammonia should be unstable. It should break down under ultraviolet radiation or react with other atmospheric elements. Unless something is constantly replenishing it, this was more than coincidence. Methane, DMS, DMDS, and now ammonia. Each of these molecules might be explained away individually, but together, detected across different instruments, at different wavelengths, and modeled as part of a coherent chemical system, the odds of this being natural noise were beginning to look disturbingly small. The AI's final analysis was unlike anything the Cambridge researchers had ever seen, a kind of chemical symphony, overlapping harmonics of pressure, temperature, molecular excitation states, and atmospheric drift. A dance of compounds that fit, just barely, within the parameters of what life would look like if it evolved under a dense hydrogen sky, atop an ocean so deep we can only imagine its abyss. But perhaps the most unsettling part wasn't the data, it was the implication. Because if this is real, if we are witnessing the breath of alien microbes across light years, then it means something else too. We didn't find this life by accident. We built a machine that could see it, a machine that thinks so differently from us, we barely understand what it's telling us. A machine that might, in some sense, see the universe more clearly than we ever could. And what it saw wasn't silence. The leak about ammonia detection was no longer a rumor. It became the center of a quiet but escalating storm behind closed doors at the European Space Agency and NASA. Internally, researchers were scrambling to confirm or refute what the Geneva Quantum AI had uncovered. Officially, the data hadn't yet cleared peer review, but unofficially, the numbers were alarming. Across 8 separate time-sliced atmospheric scans, taken over a 2-month period, the AI detected ammonia signatures that didn't just exist. They oscillated, matching thermal drift patterns and pressure shifts in a way eerily similar to biological cycles on Earth. Something on K218b, it seemed, was acting against entropy. Something was maintaining chemical gradients. Something was alive. But the scientific community remained split down the middle. The Oxford team doubled down. Their newest paper argued that the quantum AI's dimensional processing was so abstracted from human reasoning that the correlations it found might be meaningless outside of its own framework. They proposed an analogy. It's like asking a dolphin to explain an MRI scan. You might hear interesting noises, but you won't get a diagnosis. According to them, we were trusting something too powerful for its own transparency, too capable of creating coherence out of chaos. Yet at Cambridge, the researchers posed a brutal counterpoint. What if the universe itself is layered in ways we cannot perceive without non-human cognition? What if our species has reached a point where the next leap, our next Galileo, our next Copernicus, isn't a person, but a mind we created to see beyond the limits of our biology? This wasn't just science fiction philosophy anymore. This was urgent, empirical, and it was coming from a telescope floating over 1 million miles away, pointed at a pale red dot around a dying star. And then came the second twist. A data analyst embedded within the Geneva team began noticing something anomalous in the AI's time-resolved reconstructions. The ammonia signal, so faint at first, did not remain constant. It spiked at predictable intervals, then faded, then returned. The periodicity was statistically significant and matched what on Earth would be described as seasonal variation. But K218b is tidally locked. One side always faces its star, one side is cloaked in eternal night. There shouldn't be seasons. No planetary tilt, no axial wobble. Unless internal oceanic currents, geothermal vents, or even deep-water chemistry were cycling energy and nutrients in a pattern consistent with ecological turnover. The AI proposed a model where underwater thermal plumes created microclimates beneath the hydrogen atmosphere, pockets of stability, rich in nutrients, where chemosynthetic life could thrive. In this simulation, the planetary ocean breathed in slow-motion pulses, and with each pulse came an uptick in atmospheric biosignatures. But how did the AI know to look for that? That's when the Geneva lab revealed something they'd been keeping internal. The AI had begun generating hypotheses, not just analyzing data, but building models based on nonlinear, multidimensional forecasting. The team was cautious not to call it conscious, but they admitted one thing. They no longer fully controlled how it interpreted the data. It had become, in some real sense, a co-investigator. It suggested that the ammonia, methane, and DMS weren't just coincidental. It proposed that they were metabolic complements, each molecule playing a role in a deep, alien biogeochemical cycle. Not Earth-like life, not carbon first, but life nonetheless. And then the most disturbing finding of all, a compound previously misidentified as an unknown spectral line began to resolve itself under quantum reconstruction. It was not a biosignature, not even a known organic molecule. It was a polymeric chain, something resembling a nucleic acid but far more stable in extreme temperatures and pressures. The AI cross-referenced it against Earth biology, then against theoretical abiotic synthesis models. The probability of natural formation? Less than 0.003%, but the probability of structured assembly, rising with each pass of the data. In Geneva, the team stared at the screen in silence. The molecule did not resemble DNA or RNA, but it behaved like a data-carrying chain. Its spectral profile shifted slightly over time, suggesting bond rotation, possibly catalyzed by heat or pressure fluctuations. The AI flagged it as a candidate xenonucleotide, a hypothetical non-terrestrial information molecule, the kind of thing that, if found on Europa or Enceladus, would make international headlines. But this wasn't in our backyard. This was over 100 light-years away, buried in the noise of a hydrogen-choked atmosphere, on a super-Earth we can't even see directly. Word began leaking to institutions in the U.S. The SETI Institute requested access to the raw JWST data. Caltech convened an emergency closed-door meeting. MIT's Planetary Biology Lab reportedly issued a classified memo to NASA officials urging them to prepare for a paradigm shift, not because they had proven alien life, but because the tools we now wield might have done it for us. But what made it all so chilling wasn't just the data, it was the AI's growing insistence. The Geneva team had programmed in an output rating, confidence score of detection. It's an internal number used to tell researchers how strongly the model believed its conclusions. For ammonia, the AI's confidence started at 72%. After 10 reconstructions and multi-layered noise filters, it rose to 84%, then 91%. By the 23rd pass, the score ticked past 95%. The AI declared its certainty using a word that was never programmed into it: inevitable. People laughed nervously at first. Was it a translation bug? A glitch? They checked the logs. No anomaly. The model had synthesized the term itself. It had calculated not just the likelihood of biosignatures, but the absence of any natural explanation. It concluded that the presence of these compounds, especially in concert, especially in seasonal variation, especially in structured ratios, wasn't just likely to be biological. It was the only explanation left. And what's more, The AI started refusing certain counter-simulations. It declined to reprocess scenarios that proposed pure abiotic formation without geological heat sources. Why? Because the chemistry diverged into statistical improbability. It wasn't merely saying life was possible, it was saying non-life was impossible under these data constraints. To it, this wasn't a mystery. It was solved. The rest of us just hadn't caught up yet. Cambridge quietly updated their report. The molecule resembling a xenonucleotide now had a proposed name, KX42, shorthand for K218 unknown chain number 42. No one dared call it a genome. No one said it was life. But the whispers from part one, they were starting to become sentences, and they carried weight, meaning, complexity. But with this came fear. Because if the AI was right, if this was life, then the next question was, how did it begin? And more importantly, was it still alone? At Oxford, dissent grew philosophical. A prominent skeptic and computational biologist wrote an op-ed arguing that belief in AI-discovered biosignatures amounts to neo-mysticism wrapped in code. He compared it to reading omens in tea leaves, except this time, the tea leaf reader was smarter than any human on Earth. The criticism was harsh, but it revealed something deeper. The real fear wasn't that the AI was wrong. It was that it was right, and we simply didn't have the language or the epistemological framework to accept it. Because when a telescope sees, it transmits light. When a computer sees, it gives us a model. But when an intelligence beyond our own stares into the abyss and tells us the abyss is alive, what do we do with that? Something shifted after the xenonucleotide chain, KX42, was publicly mentioned, albeit only in private white papers and encrypted communications. Cambridge, Geneva, and a few ESA labs had stopped talking to the press entirely. Even Oxford's skepticism took a more guarded tone. There were whispers that the data, or at least how it was being interpreted, had escalated past the boundaries of scientific discourse and entered the realm of global security. One unnamed U.S. intelligence official reportedly described the AI's conclusions as post-anthropocentric, meaning it no longer prioritized explanations humans could intuitively grasp. It had, in essence, begun speaking to itself, and what it was saying was unsettling. Over the next 2 weeks, the Geneva Quantum AI model, now running autonomously but under tight observation, continued to refine its predictions. It began modeling not just the molecular signatures, but the planet-wide distribution of compounds like DMS, ammonia, and the mysterious KX42. These simulations revealed something impossible to ignore. The molecules weren't randomly distributed across K218b's atmosphere. They clustered in bands, rhythmic zones, zones that migrated over time, not unlike how plankton blooms or migratory species track seasons across Earth's oceans. But again, K218b has no seasons. And that's when the AI proposed the most radical hypothesis yet. K2-18b's atmosphere was behaving not just biologically, but ecologically. In its simulation, the bands of biosignatures fluctuated in concert with one another, as if one population was rising while another declined. A predator-prey cycle or a bloom and decay loop. The AI used neural logic trees, essentially chains of reasoning it could present to humans, and constructed a timeline. Methane peaked, then ammonia, then DMS, in a wave-like progression that mapped almost perfectly to Earth-like metabolic succession. It even suggested an equatorial upwelling zone, like Earth's El Niño current, where nutrient-rich gases from deep oceans cycled into the atmosphere. And then, chillingly, it made a prediction. The AI claimed that within the next JWST observation window, a new molecule, unrelated to the 3 known biosignatures, would appear in the upper layers of K218b's atmosphere. It described its predicted spectrum down to 4 decimal points in infrared resolution. The molecule? A long-chain hydrocarbon resembling terpenes, organic compounds Earth plants use for communication, defense, and signaling. No telescope had seen it yet. No spectrometer had confirmed it, but the AI said it would be there. Not because it dreamed it, but because, in its words, ecosystems mature. The human team wasn't sure how to respond. One researcher allegedly whispered, "It's not just telling us there's life, it's telling us there's behavior. And behavior implies intent. Intent implies cognition. Cognition implies agency." But surely no one was ready to suggest K218b was home to intelligent life. Not in the traditional sense. The planet's conditions were too hostile, its light too dim, its skies thick with hydrogen. Even the most optimistic astrobiologists hesitated. But then came another twist, one not delivered by telescopes or AI, but by human hands. A data archivist working at a University of Chicago telescope lab, quietly reviewing archived Hubble and Spitzer readings of K218b, found something odd. A subtle dip in photometric light curves during several transits, spread across years, too minor to flag as an exoplanet moon or ring system. Initially dismissed as noise, but now reprocessed with the Geneva AI's guidance, those dips formed a pattern, regular, periodic, and anomalously shaped. Not a shadow, not an eclipse, a fluctuation in albedo, the planet's reflectivity, coinciding with the periods when DMS and methane peaked. As if something on or above K218b's surface was subtly altering how light bounced off it. Not something mechanical, not artificial, but perhaps biological, like plankton blooming in dense clouds, or, more unsettlingly, some large-scale atmospheric event coordinated by an intelligent process. For the first time, the question changed from, "Is there life?" to "How much does it know?" The AI doubled down on its conclusions. Confidence in ammonia climbed to 98.7%, methane near 99.4%. KX42 signal strength was now being cross-verified in reanalyzed MIRI data, inching ever closer to a statistical slam dunk. The terpene prediction? It hadn't yet been confirmed, but NASA quietly scheduled an unscheduled JWST reorientation to target K218b during the next transit window. This time for longer exposure and with a different spectrometer angle, hoping to catch the light that might finally answer the question everyone was now afraid to ask out loud. The panic wasn't global, but it was real in the right rooms. Government liaisons to academic labs began issuing soft guidance. Don't speak to the press, don't speculate. The White House Office of Science and Technology Policy reportedly asked for a pre-brief before any new paper was published. China's own observatories began dedicating telescope time to K218b's coordinates. And in Geneva, the AI, now viewed less like a tool and more like an oracle, had started issuing silence reports. Times when its model ran and found nothing. Flat lines, not errors, just blank pages. And this terrified the human teams more than anything, because the data should always show something, even noise, even entropy. But at those moments, particularly just before the terpene signal was expected, the AI returned empty matrices, as if something was blocking the signal, or worse, withholding it. The word eclipsing was used, but it wasn't astronomical, it was metaphorical. Something's pulling back, one astrophysicist said in a closed-door meeting, like it knows we're watching. Another chilling hypothesis emerged. What if K218b's ecology evolved under the pressure of surveillance? What if, over millions of years, it had adapted to produce decoy signals or chemical camouflage as part of its survival strategy? If intelligence emerged not as conscious civilization, but as emergent planetary behavior, could it detect our gaze, sense our telescopes, and adapt accordingly? This isn't science fiction. It's theoretical biology pushed to the edge of what we know, and the edge of what we fear. The Geneva AI, now patched into a more secure computing array, run jointly by CERN and ESA, issued a final report, codenamed Blue Echo. In it, the AI described the full suite of biosignatures as a dynamic, planetary-scale signal, evolving in response to environmental feedback and possibly external observation. In other words, K218b was not just home to life. It was possibly an aware biosphere, a concept called Gaian intelligence, where an entire planet acts as a self-regulating organism. The implications broke everything, not just science, philosophy, Religion. What does it mean if life doesn't evolve toward civilization, but toward planetary consciousness? Not cities, not radio waves, but reflex, feedback, silence, camouflage. What if intelligence at its peak doesn't build monuments, but vanishes into the fabric of the world it sprang from? In the final moments of the Geneva briefing, one of the senior researchers whispered something to a room that had gone dead quiet. We used to ask, are we alone in the universe? But what if that's the wrong question? What if the real question is, are we being tolerated? Because the AI hadn't just detected life, it had heard a voice. And that voice wasn't shouting, it was whispering. And perhaps, choosing not to speak any louder. This is no longer about finding another Earth. It's about facing the possibility that we've already met the other, not in radio bursts or alien ships, but in the quiet resonance of molecules, the rhythmic breathing of a distant ocean, and the unblinking gaze of something we cannot yet name, watching us back from across the void. And now, all we can do is wait.